Here we look at the addition of a primary amine to an aldehyde or ketone, and specifically the 1,2 addition. Now, in adding amines to aldehydes and ketones, it makes a significant difference whether that amine is primary or secondary, and it'll give you two different functional groups for the product. Second thing you have to worry about in this reaction is the pH of this reaction is critical. Your pH in this reaction needs to be somewhere between 4.5 and about 5. Anywhere outside of that range runs the risk of the reaction not working. Turns out if your pH is too high, say greater than 5, then your carbonyl will not stay protonated. And the carbonyl needs to stay protonated because in this reaction we're working with the neutral nitrogen as the nucleophile and not a nitrogen anion. The nitrogen anion is also a strong base, and in reactions with carbonyls is likely to lead to alpha deprotonation. In fact, if you're familiar with alpha substitution reactions, such as alkylation reactions, then you may know that amine bases, such as LDA, are commonly used for that reaction. So we have to stick with the neutral amine as our nucleophile. But if your pH gets too low, say below about 4.5, then your amine gets protonated. And if your amine gets protonated, it no longer has a lone pair on it. And if it doesn't have a lone pair, it can't be a nucleophile. All right, so how does a reaction like this work? And what is the product of this type of reaction? So the overall result is that under acidic conditions at the right pH, you'll combine your carbonyl and your amine, and you'll end up with a carbon-nitrogen double bond, which is known as an imine. And there's some very, very interesting applications of imines, which I'll talk about after we go through the mechanism. So if you're familiar with reactions of carbonyls, especially nucleophilic addition to them, then it's probably going to come as no surprise that the first step in this mechanism is protonation of the carbonyl. And this allows our weaker neutral amine nucleophiles to do nucleophilic attack onto those carbonyls. From here, we get a proton transfer from oxygen to nitrogen. And then the lone pair on nitrogen adds in, forms the new double bond, and kicks out our leaving group, water. Our final step is just loss of the proton from that nitrogen to form the imine as the product. So there's kind of a neat application of this reaction, and a pretty important application for this reaction. And that deals with the following. So if we start with this molecule here, This molecule that comes from vitamin A. And vitamin A is converted here into cis-retinol. And you'll notice that cis-retinol has the aldehyde here. Over here, we're going to draw out an amino acid, this one being lysine. And so the cis-retinol that we've got there is able to bind to the NH2 of a lysine residue in aporhodopsin. And how does it do that? Well, through the reaction we just saw. It forms an imine. And that imine is once converts it to rhodopsin, and that's what allows for calcium ion transfers and allows for fission to occur.